Question 1, we have an example of a hammer hitting a steel rod, and it's connected to an oscilloscope so we can see the vibrations, which looks like this. First question is asking which control on the oscilloscope should we use to center the trace vertically. So what that means is we want to move the trace. So move the trace. So not change the way that this picture looks in terms of its size, just move it vertically up or down. And the only one that would answer that is this shifting the Y. Just to explain what the others are, this X shift is moving x-axis, and we know the x-axis is to do with time in the oscilloscope. Y gain is more about the scale on y-axis. So, for example, each square representing, say, 1 volt. If you could change that to 2 volts or half a volt, and so on. This question is also given us the scale for the time axis, and it's pointing to 50 microseconds. And in this question, we need to work out the distance between L and R. They've given us that distance, and we need to work out the speed of sound using the oscilloscope trace and this distance. So the equation being speed equals distance divided by time. And remembering that in this example, total distance traveled will be to one end and then back again. So it'll be twice this distance. Okay. And to see the time taken to go there and back again is time in contact, which is given to us in this oscilloscope trace. So from here to here is the time of contact. You could count the squares there and see it's roughly 6 squares. Okay. But 6 squares times whatever the scale is on the x-axis, which we can see it's given as 50 microseconds. And that should give you a time of contact of 3 times 10 to the minus 4 seconds. So put those numbers into the equation, and you get 5,800 meters per second. In this one, we need to explain what would happen if the steel rod was twice the length. Now, a couple of things to mention. First of all, the speed of the wave is constant, so that doesn't change. And we worked that out in the previous question. So if you double distance, okay, we understand that the contact time will increase or will double. So that means if the contact time doubles, looking back at this trace, it should double the number of waves seen along the x-axis. So number of waves on the trace. Okay. And if we look at how many that would be, well, initially it was 6 squares, so if you double that, it needs to cover 12 squares, covering 12 squares. Okay. And if you look at the entire trace, though, from there to there, the oscilloscope only has 10 squares. Okay. So it will not fit onto trace, onto display. Okay, so that should answer the, get the 4 marks for this question. Did want to get that to fit though, like understanding that the scale on the x-axis could be changed to allow that to fit. Question number 2, we have an example of a strip which is held into place horizontally, and then when it's loaded, it moves down a certain distance, and they've shown this with the distance y on the question. The very first one, we need to explain a procedure to avoid parallax error. and it's worth 2 marks. There's a couple of different answers that they accept in the mark scheme, but often whenever you're asked about making a reading which isn't directly on a display or directly next to the measuring device, so for example there's a distance apart from it, then markers are normally used. Or in this case, this pin is a certain distance away from the ruler, so you can't completely align that reading with the ruler, and we normally use set squares to do that. There is another answer in the mark scheme using a mirror, but I'm going to go with the set square method because that's the most common that usually comes up. So we can say for the first point, a set square can be used. To align with horizontal edge and touching the pin. Okay, so this is a plan view of it, and it will be placed underneath. So if you want to draw a set square here, you could probably draw it like this. So going across just below the pin. Okay, so this is below the pin. And in contact with ruler. Okay, so it aligns the pin reading to the ruler, and you can take a reading off the ruler. Okay, so just to make a final point here, set square extended out towards ruler. And read off at eye level. So this question for 5 marks is a typical question where you need to describe a procedure, an experiment to find a quantity based on an equation. And there is a format you can follow here when it comes to these types of questions. And we use the information given in the question to do that. So it's an experiment that you should design. Just like in the required practicals, we state all the variables. So we mean the independent variable, the dependent, any control variables, and then from that information talk about the graph that we want to plot and eventually how the graph gives us this answer. And we need to try and find E in this question. They've given us some information here about possibilities on what we can use as the independent variable, the one that you would change. In the mark scheme, they do accept 2, so I'm going to go with the method of changing the mass that you add. So changing the mass here will therefore mean Y changes, and you can measure Y. So the mass can be changed. And you can use numbers. For example, they say here you got when it's just the hanging mass, there's 50 grams on it, and you could keep adding 50 grams. So we could use, and it's always good to write a range of numbers for your independent variables. So I'll say 50, 100, 150, going up in 50s all the way to 250 grams. Okay, so as they say, an additional 4 50-gram masses can be added. Dependent variable, in this case would be Y, when we want to measure using the method shown in the previous question. Control variable. So there are a few control variables, and they've actually already mentioned W and T given with a fixed number. And if you remember, W and T, which is just the dimensions of the strip that's here. So you don't get marked for mentioning that W and T because that's already given in the question. You want to look at any other quantities in this equation that would need to keep constant. And the one we haven't mentioned is L. So we want to keep L and keep it as a fixed length. And let's just say we're going to use the full length, so anything less than or equal to 30 centimeters. And measure that using a ruler. Now, if you did go for changing L as your independent variable, which just means mass would then therefore need to be constant. Now, finally, to answer this question and say, well, how do we use this setup, and what do we actually plot, and how do we use this to get the value of E? So if you were to look at expecting a straight line, the y equals mx plus c equation for a straight line, we need something plotted on the y-axis and something on the x-axis. So we could say plot m on x-axis and y on y-axis. Okay. Now the equation is already rearranged in that form. We normally rearrange equations so that the quantity that's on the y-axis is the subject, and it is. So I'll write like this: y equals 4mgl cubed over e wt cubed. And I'm just going to separate out what's plotted in the x-axis so I can see what the gradient is left with. And that can be written as 4gl cubed over wt cubed e, and then the m on the outside. Only because then I could say that all of this is the gradient. Okay, because it's following now the format of y equals mx. This is on the x-axis, and that's on the y-axis. So if that's the gradient, I could just write this as an equation. So gradient equals 4gl cubed over e wt cubed, and just rearrange that to get e, which therefore would be e equals 4gl cubed divided by gradient times wt cubed, and that should get you this value of e. For question 3, we have an example of a conductive putty that you could change its shape and size, just forming it into a different shape, and they're going to say they're forming a shape of a cylinder here. So the method of using vernier calipers to measure the diameter, it says there's one problem with that. So if you've done this experiment before, the putty is not a solid object that can keep its fixed shape unless a really large force is applied to it. So the way calipers work, they need to clamp into the object that it's measuring. And putty being very soft can deform easily. And therefore decrease its diameter. For this next question, we have some readings given to us for the diameter, assuming 5 different places or 5 different orientation along the putty. And we want to show that the percentage uncertainty in D is about 2.4%. So this is a typical percentage uncertainty question where we have repeats and we have to use half the range method. So the equation percentage uncertainty is equal to the absolute uncertainty divided by the mean times 100. And for the method of repeats, absolute uncertainty is found by doing, so absolute uncertainty is equal to half times the range. And in this example, if I write this out now fully, for the percentage uncertainty is equal to a half times, well, the range is just the maximum minus minimum, and then divided by the mean. So you need to actually just show the mean calculation quickly, but I've done this before, and I work out the mean to be 33.8 times by 100, and I get 2.37%, which is roughly 2.4, as it's asking the question. This next one, we need to determine the uncertainty in millimeter cubed in the volume of the cylinder, and they've given us the length of this cylinder now. And in the previous question, we can get the cross-sectional area. So remember, it's a cylinder, so it looks like this. They've given us the length, and we know the mean diameter here from the previous question is 33.8. So we need to work out the volume to begin with. So volume is this cross-sectional area times length. So I can write that as pi d squared over 4 times length. And if you put those numbers in, so this is the diameter in millimeters, and this is the length in millimeters. I can leave things in millimeters because the question is asking us just to work out the uncertainty in millimeter cubed, so I won't change the units there. Put the numbers in and you get 6.37 times 10 to the 4 millimeter cubed. So now I need to find the absolute uncertainty in that. So if I knew the percentage uncertainty, then I can find the percentage of this number, and that will be my absolute uncertainty. So now the question is, what is the percentage uncertainty in V? Okay, so we look at the equation. If we see if V is equal to pi d squared over 4 times L, it's actually just right as proportional to d squared times L. And when we combine percentage uncertainties, we just add them when they're being multiplied like this. So we worked out in the previous question that the percentage uncertainty in D was 2.37, but in volume it's being squared, so I need to multiply that by 2. Percentage uncertainty in length, well, I could just work that out straight away from the length given to me, which is 2 over 71 times 100, and I get that to be 2.82%. Okay, so now I just add them up. So 2.37 times 2 is 4.73 plus the 2.82, and I get 7.55% uncertainty in V. So now I just need to do 7.55% of the volume, and I get an answer of 4.8 times 10 to the 3 millimeter cubed. So 100 millimeter cubed. So this next question here, we've been given an equation for finding the resistance based on the resistivity and the length. And there is a graph that's been plotted here where it's shown resistance on the y-axis and L squared on the x-axis. So just looking at this equation, rho L squared over 5.83 times 10 to the minus 5. I can see the graph is in the form of y equals mx. And if L squared is on the x-axis, that means the gradient is equal to rho over 5.83 times 10 to the minus 5. And then this one, for me to find, therefore, this resistivity, I just need to do the gradient times this number. So you have to find a gradient of this line. And a line of best fit has to be drawn here, and I'm going to try and attempt to do that. On the mark scheme, it does say that the line needs to be above the 4th point, but below the 5th point. So anything like that roughly should be fine. Draw a large triangle to show how you worked out the gradient. And also keep in mind on the x-axis, this L squared value is in 10 to the minus 3. So wherever you get your change in x's, make sure you've done 10 to the minus 3. So when I've worked this out, the gradient I got, well, the numbers I've used was 26 in the change in y. And I got 40 times 10 to the minus 3 in the change in x. And I got my gradient to be 650. So if I go back to my question, 650 times 5.83 times 10 to the minus 5, and I get the resistivity to be 3.79 times 10 to the minus 2. And the unit for resistivity is ohm meters. Question number 4. We have an example of a cylinder with some trapped air. the valve is closed so the air can't escape, and there's an object in front on top of it, P, and you can place masses on top as well to add this downward force onto the volume of air. And then they measured Y to see how that changes. So we're expecting as we add more masses, Y should go down. The first question, though, is just a mathematical relationship here that they're asking you to test. Show that Y is not inversely proportional to M. So if that was true, if it was inversely proportional, we're expecting this equation to be true. Y is inversely proportional to M. And therefore, Y times M should be a constant. So we're just looking for values of Y and values of M, and just checking if Y times M is a constant number. So I'll just show you on the graph here. If we just pick any three, at least three values to test this, you don't have to do it for all of them, but at least three values. The values I've picked were this one, 89, roughly, millimeters, 82, so the one just below that, and then 76, which is this one here. So the numbers I got, so these are the ones I picked, 89, 82, 76, and the values for M I got for those coordinates are 0.5, 1, and 1.5. Y times M, 44.5 for the first one, 82 for the second one, 114 for the last one. So we can see Y times M is not constant, and therefore relationship is not true. Not true. In this next question, we're asked to explain why P does not fall out of the cylinder when it's placed upside down, it's inverted. And we have to use some of our knowledge on pressure and forces here. So remember, the valve is closed. When they flip it upside down, this object P has a weight. So there is a force downwards trying to pull it out of the cylinder. So we know that the only reason why it's at rest there must be an upward force coming from somewhere, just from our knowledge of forces and Newton's laws, that for it to be at rest, the downward force of weight must be balanced with an upward force to keep it there. So we have to explain in this question where this upward force has come from, really. So initially, we could start by saying as P moves down, the pressure inside the cylinder decreases. And it decreases below atmospheric pressure, which is on the outside. Okay, so now think about what that means. If it decreases below atmospheric pressure, that's going to provide a force upwards, which provides a force upward on cylinder P. So, I mean, you could argue and say, well, how do I calculate this pressure? We could say it's just from the equation, pressure is force over area, and force must be pressure times the area. So the atmospheric pressure times whatever the surface area, cross-sectional area is on P. And then the point we want to make then is therefore it's at rest, P is at rest, which means upward force is equal to the weight of P. Okay. And then finally, just right up here actually, running out of space below. So if the valve opens, pressure inside cylinder equalizes. Okay, that just means air is allowed to come in again until it reaches atmospheric pressure, until equal to atmospheric pressure. Therefore, no longer upward force. Net force is weight downward and falls. So therefore it falls. Okay. In 4.3, we have to, in the same situation as in 4.2, it's inverted. And they've given us now the mass of P 0.35 kilograms. And we have to try and work out this distance y when it's in this inverted position. Okay. And we need to find this answer and approach it by looking at figure 10, and it's told us to draw a line of best fit. So you get a mark initially for doing this line of best fit. It can't be a straight line. You can see that it is curving upwards. Okay, so something like this might do. Obviously do a better job than I have here, but a curved line with an increasing gradient as you get further and further to the left. I'll extrapolate it a bit further beyond because we need to understand what's happened to this cylinder in terms of its mass. It's inverted this time. On this graph, notice we're going to the negative axis, and there is a reason they gave us the graph including from 0 to -1 kilogram. They want us to use this region here. So to understand a little bit about what's happening here, I'm going to go back to the first part of this question here. This initial distance y, so initial y is when P of 0.35 kilograms is added. Okay. So if P is removed, in other words, when you invert it, you've removed this downward force onto the cylinder now. So when you inverted it, like here, the weight of the cylinder is not pushing down onto the where this pressure gas is contained. So it's like you're removing 0.35 kilograms. Minus 0.35 kilograms when you don't have it in this position. But now that you do have it inverted, its weight is now adding another 0.35 kilograms. So in total, we have a weight of 0.35 kilograms, so G plus another 0.35 kilograms. And again, it's because initially this y shows us a value when it's here in the graph at 0. Okay, so this is the value of y over here when it's at 0. You turn it upside down, you remove the 0.35, but you also keep pulling it down by another 0.35 because the weight is pulling this object down. So in total, we have an m of 0.35 times 2, 0.7 kilograms. So I need to now read off the graph at 0.7 kilograms. And I get a value for you to do this, it's around here. And when I did this, I got a value of y. So read off the graph as 112 millimeters. There is a range of answers that they do accept in the mark scheme, so this is within the range. So it's a slightly different setup here, but part of the same question, still thinking about pressure in a gas. And we've got some gas trapped inside the cylinder with a coloured oil and a pressure gauge. So as pressure changes, the volume inside where the trapped air will change. Okay. The first question of this setup is asking us to state the error that's been made by the student making this reading, which they've said was 35.4, and what the correct reading should be. So there's a couple of different ways that the student might have arrived at 35.4. One way is that they may have just taken the reading at the top of this oil, or what we call the meniscus, whereas the reading should have been taken from the bottom of the meniscus. So you could say reading taken at top of liquid and should be taken at bottom. And you say meniscus is the word for that. It's not required, but clearly describing the meniscus is fine as well if you don't use the word meniscus. And if you do that, the reading should have been 35.8. Now, another possibility that could have happened where this error could have been made is that the student did take a reading at the bottom of the meniscus, but the scale was wrong. So these individual smaller squares here should have been 0.2, but the student may have read those smaller scales as 0.1. Add in, student may have read smaller divisions as 0.1 when it's actually 0.2 centimeter cubed. In this question, we want to see if the gradient can confirm if Boyle's law is being applied. So we do have log graphs here, and we need to use some of our math knowledge on dealing with log graphs and log equations. But I'll start with the familiar Boyle's law. We know PV equals nRT, or you can say nKT. If I try and rearrange this with V, I get V equals nRT over P. And if I were to log both sides now, log of V is equal to log of nRT over P. Using our log rules, I could separate this as log V equals log nRT minus log P. So you can start seeing that I'm starting to get this format now of where I have a straight line equation of following the format of y equals mx plus c. So I'm just going to rewrite this as log V equals minus log P plus log nRT. Oops. Because I want to see it in the form of y equals mx plus c. You can see log v is on the y-axis, log p is on the x-axis, and look, the gradient is equal to minus 1. Okay, so the maths tells us that if this relationship is true, the gradient I should be getting for a log v against log p graph should be minus 1. So you could work out the gradient of this line between any 2 points that are quite far apart. And when you work at the gradient of line, you see it's minus 1. So it's confirmed. Again, they do accept a range of answers for this gradient, but it will be around minus 1. Now, for this question, they want us to work out the corresponding value of volume for when the pressure is this value of 3.4 times 10 to the 5 pascals. Now, this number, 3.4 times 10 to the 5 pascals, is written as 0.34 megapascals. And the reason why I'm using it in megapascals, because in the graph, they've taken these log values of pressure in megapascals. So I'll keep that as that value here. Now, we know the equation of the line is, as written here, log V is equal to minus log P plus a y-intercept, which I'll just call C for now. I know it's log nRT, but I'll call C for now. I don't know this y-intercept, and be careful to, a common mistake might be that saying that this is the y-intercept. Yep, that's wrong. That's not the y-intercept, because you can see the graph here doesn't start at 0. It would carry on further. So this is not the y-intercept. Okay. So then how else do we find the y-intercept? We should hopefully remember our knowledge of straight lines from maths, in that if we just have any coordinate on this line, I could put the numbers in and therefore find my missing y-intercept. So the number I will pick here, somewhere where I can see exactly it crossing a point that's easy to read off. I'm going to pick this point here. So the coordinate of that point I have is minus 0.87, and on the y I have 1.45. So I'm going to use that for my x and y values for this equation. So that's written as 1.45 equals minus 0.8, go back, 87 plus c. So just rearrange this, the minus and the minus make it a plus. You get your y-intercept to be 0.58. So I have my y-intercept now, so I can write this equation in full. Plus 0.58. So now that I can put these numbers in, I can find out what log v is. Minus log of 0.34. Remember that was what our pressure was that we're trying to find this volume for. Plus 0.58. Now I get log v when I put this in the calculator as 1.05. So again, knowledge of logs, in your calculator log by default is base 10. So if I do 10 to the power of 1.05, and that should give me the value of v. Okay, do that and you get 11.2 centimeter cubed. So final question, state one property of the air that must not change in order for Boyle's law to apply here. So again, reminding ourselves of Boyle's law, PV equals nRT, and it should be constant for Boyle's law. Okay, so if we look at the right hand side, everything here should be constant. So in other words, temperature must be constant. I mean, you could also say like the number of molecules of gas is constant, but if it's a sealed container, which it is, then the temperature is constant. In the marksman, they do accept two ways to control this. You could change the pressure very slowly, or what might actually be better to do is wait for liquid to settle, as in the oil level. Yep, so if I go back and show the diagram here, this level is going to move up and down depending on pressure changes, but it might initially move up or down when you change the pressure, but then it will take time to then settle to a correct reading as temperature equalizes back to the temperature it was before. Okay, so wait for liquid to settle as temp equalizes to room temp. Okay, before taking reading.